Hello class, today we're going to start using the finite element MATLAB code provided by your book. This code is based on the same 6 steps that we have followed in order to solve problems by hand. Let's recall these 6 steps. The first step is pre-processing. In this step, we subdivide the structures into elements, assign node numbers and element numbers. The second step consists on writing down the stiffness matrix of each element in global coordinate system using global numbering. The third step is the assembly. In the assembly, we assemble the element stiffness matrices to form the global stiffness matrix for the entire structure using the node element connectivity table. In the fourth step, we apply the boundary conditions. In the sixth step, we have used the reduced equation method for solving the unknown displacements. However, last class, we saw that there are other 2 options that can be used as solvers. And in the sixth step, we compute the unknown nodal forces. So let's recall some basics. The element stiffness matrix that we have derived in class for 1D problems consists of a constant Ke, which is equal to Ea over L, times the matrix 1 minus 1 minus 1, 1. And the solution technique used is based on partitioning, in which we group the degrees of freedom by essential or free. Essential are those nodes that we know, and free are the nodes that we don't know. And based on that, we can partition our global system of equations, and we end up solving 2 equations with 2 unknowns. In this case, the unknowns are the reaction forces and the free degrees of freedom. And then we expanded our element to 2D. And in 2D, this is the formulation for the element stiffness matrix, which consists on some cosines and some sine terms. And for 3D trusses, we derived the formulation last time, and also depends on some angles. Before we start looking into the MATLAB code, let's start reviewing what a MATLAB function is. And for that, we're going to use an example. Let's say we want to create a function that computes the area of a triangle given its base and height. Let's say we want to call this function area. If we call this function area, that implies that the name of the file also needs to be area. And the .m, it's an ending for a MATLAB script. When we start our function, we need to write the word function. Next to function, you can have a set of outputs or a single output. In this case, you only have one output, and this output is A. In order to get this output A, you need to fit in to this function either both the base and the height. So from here, A is the output of the function, B and H are the input of the function. And then you can call this function in another .m file as A equals area, and you need to pass the base and the height. So let's do it in MATLAB. So you can open MATLAB and then write a new script. So we said that we need a function that we're going to call area, in which our output is going to be A for area, and it's going to have inputs B and H. We know that the formula for a triangle is 0.5 times base times height. And then we have to save this function as area. And MATLAB will already give you a hint that you have to save this script file as area. Now I can call this function from the command window. If I say A equals area 2, 5, it's going to tell me that my area of the triangle is 5. And we know that is true because 0.5 times 2 times 5, it's 5. Now I can call that same function from another script file. So let's say I want to calculate area in another file. So I have to say A equals area, and then B1, B2, just to show you that the function can work by defining variables in another script. So let's say B1 equals 2 and B2 equals 4. So if I save the script as other script and I run it, I'll get that area A equals 4, which is right because 2 times 4 times 0.5 is 4. Your workspace also shows you the value of A. So let's modify this to 10 and 20. And let's run other script. Let's save it. So if we run other script, we see that the area changes to 100. So that's the value of the area. Let's return to our PowerPoint presentation. Now let's complicate the function a little bit by asking to not only give the area, but also the circumference, in this case of a circle. So our goal is to get the area and the circumference of the circle given the radius r. So again, A and C will be the outputs. Now, because in this case you have more than one output, you need to put a bracket next to function and close the bracket after you write all your outputs. Then you can call the function in another .m file or from the command window as AC equals area r. So let's give it a try. So let's say I want to modify this function area. Now I want to make it a function of the radius, and I'm gonna get the circumference and the area. We know that the circumference of a circle is 2 times pi times r, and the area of a circle is pi times r squared. So now we save this, and in order to call it from the command window, now I have to say CA equals area, and let's say area of 2, radius 2. So it gives me an area and it gives me a circumference. And it happens that for this case they are the same. Now if I call it from another script, now I need to change this. Let's say r equals 5. And now I want again the circumference and the area. And now I have a new area and a new circumference. Our finite element code in MATLAB consists of several functions connected together. Today I am going to introduce you to the MATLAB code for truss problems through this example. In this example, you have 2 truss elements with elastic and cross-sectional area being constant. These 2 ends are pinned. This distance is L and this distance is L. And you have an external force acting on the 3rd node in the horizontal direction with magnitude 10. So at this point, you need to go download the truss program from Blackboard. So within Blackboard, in your course, go to MATLAB Codes. In MATLAB Codes, you're going to see 2 zip folders. First, download the truss program zip folder. And I'll transfer this to the desktop, and I have created a folder called FE class codes. So I'm going to put it here and I'm going to unzip it. So extract all, and the files have been extracted here. Now, as you can see, the code consists of several MATLAB scripts. You need to make sure that you change your MATLAB directory so it coincides with the location of your code. In this case, I have saved my finite element code on my desktop. So I'll have to go to desktop and FE class FE codes, and then I have to go to trust program. And then I had another folder called trust program, which I have to open in order to see all the files. So at this point, you should be able to see these files within your folder. Now let me explain you the function of all these files. Let's go back to our presentation. This is the general structure of the finite element program in MATLAB. Trust is the main file. Trust is in charge of defining global variables, pre-processing, assemblage, solving the finite element problem, and outputting results. Within Trust, you start by defining global variables. So if you open the Trust code, you'll see that the first lines here have a percentage. Whenever you include a percentage, that is a comment in MATLAB, and the code doesn't read these lines. It's just used as reminders or to write any other relevant information. Then these two commands are important because you want to make sure that all variables have been cleared and that any information on the command window has also been cleared. So the first thing that trust.m does is that it clears any information in MATLAB. The next step is that trust.m will create some global variables. In order to create some global variables, the trust.m file calls include_flags, as you can see here in our general code structure. So trust define global variables through include flags. Let's see what the include flags routine has. So these are global variables. These are variables that you can call in any routine that is used within this code, as long as you include the command include flags. The reason why you want to use this form is because you don't want to be passing all these variables that may be needed in different routines through the function command. So this avoids writing a large set of input parameters. Now, these variables will be available in all functions without passing them through the function command. So there are some variables that, as we're going to see, can be very helpful to allocate as global variables. Then trust goes through the pre-processing step. So if we continue on the trust.m file, we saw that first it cleared all previous information. Then it created some global variables. Then trust.m will proceed with the pre-processing phase. And as you can see in this pre-processing phase, you're going to have three outputs, K, F, and D. And you're going to obtain them by calling the function preprocessor. So again, trust created some global variables through include flags, and then it's calling preprocessor in order to initiate the pre-processing step. Now this is how the preprocessor.m file looks like. And in here it says that preprocessing reads input data and set up the mesh information. So as you can see, the first step within this function is to include flags. Then the second step is to input file to include all variables. Okay, so from preprocessor, we're going to go to input file, as you can see in our general structure. So again, let's follow these steps. From trust, we went to define some global variables. We went to pre-processing by calling the preprocessor.m command. And then within preprocessor, we have called the input file. Now, in this input file, we include the general information that the code needs to solve the problem. That includes geometry, material, and loading. At this stage, no calculations are required. We just provide all the information that we know to the code. So there are some variables that we need to make sure they are right or modify if needed. So let's look at this example that we are considering. The first variable, which is NSD, it's the number of space dimensions. Here we are in 2D space, and that's why this variable is 2. Then we want to know how many number of degrees of freedom we have per node. Since we are in 2D space, we can have a node moving in both the X and the Y direction. And we're going to have 2 degrees of freedom per node. Then we want to write what are the number of nodal points. In this case, we have 3 nodal points, 1, 2, 3. So the number of nodal points is 3. Then we want to proceed to write the number of elements, which are 2, 1, 2. Then we want to let the input file know how many number of nodes per element. So there's 2 nodes per element. Then the number of equations can be obtained by multiplying the number of degrees of freedom per node, which is 2, times the number of nodal points, which is 3. So we have a total of 6 unknown equations. The next step consists on defining the element area for each of the elements. In this case, let's say the area equals 1 for both of the elements, as they are constant. The size of the array that stores the element area information has to be equal of 2, because we have 2 elements. And since they are constant and equal to 1, we're just going to write 1 twice. Then we need to proceed to write the information of the element's length within this array. And in this case, element 1, defined here, has a length of L, which we're going to define as 1. And then that means that element 2 is going to have a length of the square root of 2, just by defining the length of this hypotenuse. Then we're going to define the angles of our elements. Element 1 has an angle of 90 degrees, while element 2 will have an angle of 45 degrees with respect to this x-axis coordinate, in which we moved from the first node to the second node. Let's assume our elastic modulus is constant and equal to 1. So that means that element 1 has elastic modulus of 1 and element 2 has an elastic modulus of 2. Then the input file is asking us to input the prescribed displacements. In this case, the prescribed displacements correspond to these 2 nodes which are pinned. Each of the nodes has 2 prescribed displacement, as it has a restriction in the x and in the y direction. That means that d1x, d1y, d2x, and d2y are all equal to 0. nd is the number of prescribed displacements within the model. In this case, it's 4. Then we need to assign the forces. In this case, we have an external force on the third node. The degrees of freedom corresponding to that node are 5 and 6. 5 would contain the information of a force in the horizontal direction, and 6 will contain the information of a force in the vertical direction. In this case, we only have a force in the horizontal direction, and we'll write that F of 5 equals 10, while F of 6 equals 0. The next 2 options are just for plotting purposes. Plot underscore truss equals yes will create a plot with the truss elements, and plot underscore not will create the nodal points of the truss. In this case, they are both defined as yes, and we should keep it that way in order to get an illustration. Now you can see that from the input file, we call another routine. In this case, is truss mesh. Again, let's go back to the sequence of the code. From truss file, we call the include underscore flags, which define global variables. Then we call preprocessor.m. Within preprocessor.m, we call the input file. In the input file, we define general information that we know prior to solving the code. And input file calls truss mesh. So let's go to truss mesh. So this is the function truss mesh. Within this function, you see that include underscore flags, it's called. That means that all those variables that are defined in include underscore flags can be updated or be available within this function. Within the X array, we're going to define the X coordinate of the nodes. In this case, let's say the origin is right here at node 2. That means that the X coordinate of node 1 is 1. The X coordinate of node 2 is 0. And the X coordinate of node 3 is 1. The Y coordinate of node 1 is 0, of node 2 is 0, and of node 3 is 1. The next step is to define the connectivity array. Now, in this case, IEN contains the connectivity information. In this case, each column represents an element. And the first row is the first node of that element, and the second row is the second node of that element. In this case, we have two columns because we have two elements. Element 1 consists of nodes 1, 3, so that's why we have 1, 3 in column 1, and element 2 consists of nodes 2, 3. That's why we have 2, 3 in column 2. Then we go to plot the truss by calling this plot truss routine. So again, let's go to our general sequence. So from truss, we went to define global variables to preprocessing. Within this preprocessing, we have called preprocessor, input file, truss mesh, and now plot truss. Let's see what plot truss does. First, it includes flags, and then it asks if you want to plot the truss. In this case, we have said yes, so it's going to proceed to plot the truss. The truss elements are plotted within a for loop. This loop will be accessed a total of NL, which corresponds to the total number of elements. So I is going to vary between 1 and total number of elements. For the first time, it's going to create an XX array, which is going to contain the X coordinate of the first node of the first element and the X coordinate of the second node of the first element. Remember, I here corresponds to the first element, and IEN corresponds to the connectivity matrix. So right now we're accessing the information of the first column of the connectivity matrix. Then YY will write down the Y coordinate of the first node of the first element and the Y coordinate of the second node of the first element. Then the code proceeds to drawing a line between points X, X, Y, Y. The second step writes the node number on the plot for each of the elements. So for the first element, it's going to write node 1 here and node 3 here. And for the second element, it's going to write node 2 here and node 3 here. And this is just a regular plotting function. Once the code exits plot truss, it goes back to the preprocessing file. In this preprocessing file, the next step is to generate the LM array. And this is an array that will help to assemble the global stiffness matrix. Let's recall our connectivity matrix. For this case, it's going to be of size 2 by 2 because we have 2 elements and each of the elements has 2 nodes. Now, node 1 has degrees of freedom equal to 1 and 2. Node 3 has degrees of freedom equal to 5 and 6. Node 2 has degrees of freedom equal to 3 and 4. And node 3 has degrees of freedom equal to 5 and 6. So in this case, the LM matrix contains the degrees of freedom associated with each element in sequential order. So these are the degrees of freedom associated to the first node of that element, and these are the degrees of freedom associated to the second node of that element. The next step is the calculation and assembly of element matrices. This is done within a for loop. For e equals 1 to number of elements. The first thing that is done within this for loop is to call truss lm, which calculates the local stiffness matrix. So again, here within our sequence, we go to our third step, which is assemblage, and then we have called the truss lm. So let's recall that we have done 1D and 2D trusses. If you are in 1D, you have one stiffness matrix. If you are in 2D, you have a bigger stiffness matrix. This function is called truss lm, and as we can see, it should have the element number, the elastic modulus, the area, the length, and the phi angle if it was a 2D truss. However, most of this input have been defined in the input files and are available through the command include flags. The output is the local element stiffness matrix. Again, recall that E, A, L, and phi are passed through the global variables. So in this case, the function becomes written as Ke equals truss lm of E. Again, this is the input, this is the output, this is the name of the file. And this is what you see if you open the trusslm.m file. The first thing that is done is that include flags with all the information available for the global variables. Then it calculates the constant, which is independent of 1D or 2D trusses, as it's always the area times the elastic modulus divided by the length. Then it has an if statement to check if you're in 1D or 2D. If you are in 1D, the element stiffness matrix is the constant times 1 minus 1 minus 1, 1. If you are in 2D, you have to use this 4 by 4 matrix, in which this terms depends of cosines and sines. There's a small step to convert the degrees to radians by multiplying the phi times pi divided by 180. Then s equals sine p, c equals cosine of p, and s squared equals s raised to the second power, and c2 equals c raised to the second power. And this is the 2D stiffness matrix that we have done in class. Now, this conversion can be avoided by using sine d instead of sine and cos d instead of cos. The next step is to use the information from the local element stiffness matrix and put it within the global stiffness matrix. So the truss.m calls assembly, and within the assembly you use that LM array that contains the degrees of freedom of each of the elements in order to assemble your global K. And this routine you don't have to modify, but it's just based on what we saw in our very first lectures. All this routine is doing is assembling the global stiffness matrix. Let's recall this example that we did in class, in which we had two elements. And since we had 3 nodes and 1 degree of freedom per node, the global size was 3 by 3. Let's recall that in class I used a notation on top of the element stiffness matrix, which was not numerical. And it was U3, U2, U3, U2, U2, U1, U2, U1, U1, U2, U3. And I will use that in order to know where should I go and put my local information into my global information. However, computers cannot recognize that notation, and that's why we have converted that information into this LM array, in which now we identify it by the number of degrees of freedom. In that case, the third node has the third degrees of freedom, the second node has the second degree of freedom, and so on. So this is just used to assemble the global stiffness matrix. And again, you don't have to modify this routine, but I'm just want to let you know where it came from. After the assembly it's performed, the next step will be to solve the system of equations by calling this solve_dr file. So after the assembly, you call the solve_dr file, which is the fifth step of your solving process in finite elements. Recall that we had defined an nd variable that identifies the number of prescribed displacements. And in this case, since it was easy to group the essential degrees of freedom and the free degrees of freedom, we can solve this problem using the partitioning approach. Now here you can see that once the K is assembled, you can identify KE, KF, KEF, F of F, and D of E by just knowing the number of prescribed displacements. Then the second step will be to find the degrees of freedom that are free by using the second equation. And then based on that, you reconstruct the global displacement by putting together the essentials with the free. Then you can compute their reactions by using the second equation as we have done in class. The fifth step within the trust.m function is to call the pause processor. I have gone through all the routines of the code. This program replicates our solution approach by hand, which we have followed in class. Now let's try to modify it in order to obtain a solution for a different problem. This is the problem of consideration. In this case, the elastic model is 30 times 10 to the 6 psi. The cross-sectional area is 2, and this is the truss in consideration. You have 4 nodes and 3 elements. Let's modify the code. In order to modify the code, the only thing that you need to change is the input file, because then the other routines are only there to solve the problem, and the solution approach is the same. So let's open the input file. So let's see, what do we have to change? So the number of space dimensions stays the same because I'm still in 2D. The number of degrees of freedom per node stays the same because there are 2 per node. The number of nodal points in this case changes to 4 because I have 4 nodal points. The number of elements in this case changes to 3 because I have 3 elements. The number of nodes per element is still 2. Now let's modify the area array. So the size has to be of 3 because we have 3 elements and each of them has an area. And the area is equal to 2 for each of them. So this becomes 2, 2, and 2. Now let's change the length. The length of 1 is 10. The length of element 2 will be the square root of 10 squared plus 10 squared, and the length of 3 is 10. So let's change this to 10 square root of 200, and the last term is 10. The square root of 200 is 14.14. Now let's define the angles. The angle of 1 is 90. The angle of 2 is 45, and the angle of 3 is 0. Now let's define the elastic modulus. So this is 30 e to the 6, 30 e to the 6. We can take it out because they're all the same, and it's going to multiply each of them like this. You can also have written 30 e to the 6 in each of these entries. The number of prescribed displacements in this case is 6 because we're going to have 2 more because the third node is prescribed. as well. So we can put here for reference D3x and D3y are also prescribed, and the number of prescribed is 6. Now you have an external force in node 4, which corresponds to degrees of freedom 7 and 8. Now there's no horizontal force, and there's only a vertical force of 10,000 pounds. So we'll change this to 7, 8. Now 7 is 0, and this one is 10,000. We want to plot the truss, and we want to plot the nodal points. We save this information. Then we proceed to changing the truss mesh, because that has the nodal coordinate information. Now in this case, we need 4x coordinates because we have 4 nodal points. And if we define the origin at node 4, so let's define the origin at node 4. That means that nodes 1, 4 have coordinate 0, and nodes 2 and 3 will have coordinate 10. So this will become 0, 10, 10, 0. And then in terms of y, node 1 is going to be at 10, node 2 is going to be at 10, and then node 3 and 4 are going to be at y equals 0. Now we need to make an adjustment because this information is in feet, while your elastic modulus and your cross-sectional area, it's in inches. So we'll also have to go change the length array, but we'll proceed to do it in a few. So we said that in the y, we're going to have 10, 10, and 0, 0. Now let's put here 12 times, because there's 12 inches in a foot, and 12 times. And let's save it. And in our input file, let's do the same. Because this information was in feet, we need to multiply that information times 12. Okay, let's go back to define our connectivity array. Remember, we have 3 elements. Element 1, it's going to be composed of nodes 4, 1. Element 2 is going to be composed of nodes 4, 2. Element 3, it's going to be composed of nodes 4, 3. And we save it. Now let's recall, in order to run this code, we have to run it from truss, because truss calls all the routines needed. And let's see if we did it right. The answer that I obtained, it actually is not making sense. And the reason being, it's because I would expect my element 1 to have a tensile force. But in this case, my element 1, it's having a compressive force. So that means that I must have made a mistake in my input file. And if I go through my input file, and I'll see that my force 8, it's equal to positive. Well, it should be a negative value because the force is going down. Now let me make that adjustment by saving it and running my code again. And now I have a solution that makes sense, because now I have elements 1 and 2 in tension and element 3 in compression. Let's see if that makes sense. Yes, element 1 is expected to elongate, element 2 as well, and element 3 might shorten because this node might move a little bit here. And let's look at the displacement of node 4. So for that, we can look at D. So D contains our displacements, And you'll see that the seventh node indeed moves in the positive direction. So that means that the element 3 will shorten, and that's why you need to get a compressive stress. We haven't gone over the post-processor file, which is the file that's calculating stresses, and it calculates the stresses for every element. It checks if you are in 1D or 2D. If you are in 2D, which this is the case, you need to follow this multiplication, in which there's a constant and then there's an array that depends on cosines and sine multiplied by the degrees of freedom corresponding to the current element. And this is what we did last class. So it's just a computation done in MATLAB according to what we did in class by hand. Now the problem with this code is that can only solve problems whenever you have your essential degrees of freedom grouped. So we need to modify the solver in order to give us freedom of the problems that we can solve. So that's why you have to go download the modified TROS program in order to change the solution strategy. So download it from Blackboard, and ideally put it in the same folder that you have used for your other code. So now let me go back to MATLAB and let me access now tros.m, and within tros.m you'll see that I made some modifications. Within these modifications, if you follow them closely, they are the steps that we followed last class. And let me get the notes from last class. So these are the notes from last class. In last class, we derived the formulation needed to calculate the local stresses or the stresses in each element. And this will be the formulation depending on a constant, which is E divided by length. And then this array consisted of cosine and sine terms multiplied by the degrees of freedom of that corresponding element. And if you look again at your code for post-processor, this is what it's being done. You have that constant, which in this case the constant is just the elastic modulus divided by the length, as you can see, and then you have this array times the degrees of freedom, and this is the constant times this array of cosines and sine times the dE, which dE is only obtaining the displacement at that current element by calling the degrees of freedom corresponding to the current element. But let's look at the solving strategy of this TROS folder. So in here we have deleted. So in this case we're not calling the solve.dr, but we are coding the approach we followed last class. So last class we said that you can follow a deletion technique based on these steps, in which you already know some degrees of freedom, and you want to take advantage of that information by putting the product of k and the known degrees of freedom on the right hand side, and then by letting the degrees of freedom equal the value that you know, and then based on that you can just do a backslash operation. Now in order to do that, we're going to implement two more changes. Now in your input file, instead of telling the code which are your prescribed degrees of freedom, we're going to use a flag system. This flag system is going to help us identify the locations in which you have a prescribed displacement. Now let's make a small change in order to illustrate how independent the solver is of the node numbering. So now we're going to make this one node 3 and then this one node 4. That will change our information in our code, specifically on your truss mesh file. Now your x is going to be equal to 0, 10, 0, 10. Your y it's going to be equal to 10, 10, 0, 0. Your connectivity array is going to be 3, 1, 3, 2, and 3, 4. Within your include flags, you're going to include now 3 more variables, which are flags, e underscore bc, accounting for the essential boundary conditions, and nb underscore bc, accounting for external nodal forces conditions. So let's go to the input file. Within the input file, we're going to assign a flag of 1 if there's an external force, and a flag of 2 if there's a essential boundary condition. In this case, there's a force acting in degree of freedom 6, because if you look at the degrees of freedom here, so this will have degrees of freedom 5 and 6. So degree of freedom 6 has an external load, and then degrees of freedom 1, 2, 3, 4, and 7, 8 are prescribed. So that means that flag 6 equals 1 because you have an external force. Flags 1 through 4 have 2 because you have a prescribed displacement. Flags 7 to 8 have 2 because you have a prescribed displacement. Then in n underscore bc, you put the magnitude of that external force, which in this case is minus 10,000 pounds, and the magnitude of your essential boundary conditions in 1 to 4 and 7 to 8, which are zeros. Then you go to truss, and you'll see that in here it's just applying the solution method that we described in class. And if you run it, we should obtain the same answer as last time. And as you can see, the answers are the same as last time, even though our node numbering and our solution approach was different. Now, if you were to implement the penalty method, which is required in class, you would still use the flag system, but now recall that within the penalty method, wherever you have a prescribed displacement, you had to assign a beta amount in that location of the prescribed displacement, and in the right hand side you need to multiply the magnitude of the prescribed displacement times beta. So how would you do that? Let's go back and look at the code. So the modifications need to be whenever you have a prescribed displacement. In this case, wherever you have a flag of 2. You don't need these 2 steps, but whatever you had a prescribed displacement at that degree of freedom, you have to put a beta. So let me put a beta. And then in that same equation, you had to multiply the prescribed displacement times beta. So again, this will be KNN equals beta. And in that same equation, you need beta times the described displacement. And this is beta times the prescribed displacement magnitude. Now let's put beta outside here, a magnitude for beta. So we said we want something very big. So if E equals 30e to the 10 times 6, if E equals 30e to the 6, let's make it bigger than that. Let's make it 1e to the 15. And we should get the same solution. And guess what? We get exactly the same solution. So this is it for class. I just want to let you know that what it's coded is what we went over in class. And if you need more time to break it down to see what the code is doing, I would suggest printing each of these routines and trying to write next to the codes by hand what it's each line of code doing. But I hope this is helpful. See you in class on Monday.